Hello everybody, good morning. Welcome to 528. My name is Birgit Kaufmann and I'm an assistant professor with a joint appointment in mathematics and physics. I'm teaching this course for the third time and I'm really excited about it. I think it's almost the nicest and most interesting course you can take in mathematics. So I'm really looking forward to teaching this, and I hope I can convey this enthusiasm to you also. This is a little bit an unusual setting this semester because this course is going to be taught in 3 different sections. So there's the section that is sitting in this classroom here. We also have what is called on-campus distance learning section, which are students that are on campus but who are just watching the videos, and I would like to welcome those especially. And we also have a real distance learning section of people sitting all over the country who are mostly working full-time jobs and taking this class in addition to that. So I really admire that. And I hope that I can make all of those part of this course. So I have set up a few resources. First of all, all the information is given on the syllabus that I've passed out, and I've sent this by email to all the other students. So let me briefly go over this, and then if you have any questions, there will be time to ask later. So you have all my contact information on the syllabus. Maybe I should start to write something like this. On this. So I'm teaching the first time with a smart board, and I hope it will go smoothly. Let's see how it works. So my contact information is all on this sheet. Let me just write this down. Let's see if this works. Can you see this on your screens? Okay. So my name is Birgit Kaufmann. Let me write that again. And you can reach me by phone or by email, and this is all on the syllabus. And I strongly prefer email. I'm really an email person. I have official office hours that are right after this class from 10:30 to 11:20. 10:30 to 11:20, and if you can't make those hours, you can always send me an email and meet me at some other time. I think it's difficult to pick a time that works for everybody. The course text will be the Kreisig Advanced Engineering Mathematics, and we will be using the 10th edition. So I think in the past we have always used the 9th edition, but since this is new, I hope it has improved solutions. With the 9th edition there were some problems, some solutions were wrong, so I hope they have improved this. So we will see how that goes. I have set up a course website. Let me see if I can switch to that. Can you see this? It's on the mathematics homepage, and it consists of 2 pages. So this is the first page that explains basically how everything is set up, right? And you have all the details again that are contained in the syllabus. And then you can click on schedule and homework assignments on top of this. And it takes you to another page that talks more about the homework. And you see the schedule, and this is exactly the same thing that you have on the last page of your syllabus. But what is different on this web page, I will always put in the due dates of the homework. Okay, so this brings me already to homework. So there will be weekly homework that will usually be collected on Wednesdays, and we will start next week on January 18th. So not this Wednesday, but next week Wednesday. And I will collect the first homework, which consists of all the problems that are assigned to lessons number 1 and 2, which we will have covered by the end of the week. Okay, so as a general rule, I always give those problems as a homework assignment that we have covered in the previous week. Okay, and I will update the schedule on this homepage as we go along. So you already see the first homework is fixed, and I will put this also on Blackboard. So Blackboard is the second resource you can use for your information. Okay, so this is where you can find the homework, or you can go to Blackboard. And right now the Blackboard page is pretty empty, right? So you will see the syllabus, you will see lecture notes. This is where I post copies of what I write during the lecture, so you don't really have to copy everything, right? You can just go online afterwards and download my notes. So in this way it gives you more time to listen, which is very important, I think. I will post homework solutions for you, and under exams you will find sample problems for the exams and so on. Okay, so we come to that. There's also an announcements page, and it's weird. I thought I had put in some announcements already. Let's see if I can see them on a different view. Yeah, strangely enough, I can see them now. Okay, so this is where I will post the homework assignment. So the homework assignment will be in two places, right? It will be here and it will be on this official course website. I will try to keep the calendar up to date also. So there's a calendar that shows you when the homework is due, when the exams are, right? So I will try to put this all in. And what I think is very important to know is this discussion tool. And I know that in the past it was very lively and very widely used in this course. So this allows you to interact with fellow students in this course. Everybody, right? Not only the students that are sitting in the classroom, but with all the students that are registered to this course. And I would encourage you to go online and seek some discussion and also discuss maybe homework problems, right? I think it's very important to be able to work in a team, especially in your profession, right? And this encourages some interaction with other students, and I've seen that there was a lot of discussion going on. I'm not always looking at this on a day-to-day basis, so it's really a tool for you where you can discuss with your fellow students. Sometimes if I really see a big mistake, I would go in and correct it, right? But it's not something I would monitor every day. So it's really for you to have some interaction, some social life, okay? And if you like, you can also, I think you can also put in your profile, if you go to rosters, you see my picture and you see my information, but you can also create your own homepage for the others to see, okay? And then I think you can look at your grades. So there is a grade book. I can't really show you the grade book as the demo student, right? So this page will show you all your grades, and it's always good to double check, because I think we have about 160 students altogether. So sometimes there's just a slip in information, right? I will ask the TAs to put in their grading results directly into Blackboard, but sometimes they forget or they get confused, so it's always good to double check, okay? All right, so these are all the resources that are there. Let's go back to the Smart page. I think I've covered a lot of the syllabus already. So for the homework, there are different procedures to collect the homeworks. Those who are sitting in class, I would just ask you to turn in paper homework on Wednesday during the class or after the class, okay? For those who are taking the course online, if you could just take your handwritten papers and scan them and send them to these two emails that are for the on-campus distance learning and for the off-distance campus learning sections. And I would like to ask you to send them in by midnight on Wednesday, okay? So if the due date is Wednesday, send them before 11:59 or before midnight, okay? And please make sure you name the file as is stated here, last name, first name, and so on, okay? We will have 2 midterms, and this is very important. You should mark the dates already. These are evening exams, and they will be common exams for those students sitting in class and those on-campus distance learning students. So we will have 2 midterms. And you can already put them on your calendars. The first one will be Wednesday, February 15th. And that will take place in Lily 11:05. And I think I didn't put the time, but the time is on Blackboard already, 6:30 to 7:30 p.m. So it's an hour-long exam on February 15th. And then we will have another one, which is also on a Wednesday, April 4th. And this is in a different room. So it's WTHR 200. And it is at the same time, 6:30 to 7:30 p.m. Okay? So I'll tell you more about the exams when we approach that time. Okay, then there will be a final, comprehensive final in finals week. The date is not yet fixed. And the grading of the course, I should say, that relies on the exams and on the homework. So we will have the total homework that counts for 100 points. And I think I said I would drop the 2 lowest homework scores. So I'm not accepting any late homework, but I will drop 2 of the lowest scores. So if you ever miss 1 homework or 2 homework sets, it doesn't really affect your grade. Okay? So I will drop the 2 lowest scores. And then we'll have the midterms, which count for 100 points each. And we'll have the final, and that's more important. It's 150 points, so that we have a total of 450, right, for the course. And this is where I would base my grading upon, okay? But I can already tell you that I'm not a really strict person, right? I don't like giving bad grades. I think it's very important to have some success, okay? So don't worry too much about your grade. I think it's really important that you worry about the mathematics and that you understand things, okay? It's not so much about exams and grading. All right, so whenever there's anything that you don't like, please come forward and tell me, okay? You can also, if you don't like to be recognized, you can slip me a piece of paper in my mailbox or use my answering machine or whatever to be anonymous, right? But if there's really anything that doesn't work for you, let me know, okay? I'm always telling about one course where I was working on the blackboard and people told me in the final evaluations I was standing in front of my own writing, right? So that was really stupid, not to say it just in the first lecture, but to wait for a whole semester and to put up with that. So please tell me if there's anything you don't like, okay? Do you have any questions so far? Okay, if not, yes?
Can in-class students also submit their homework by email?
No, that's not possible. So you're supposed to bring it in. So that's an advantage or disadvantage of being in class. But we have different TAs working on different homework sets and different emails, so it will be all mixed up if we start allowing that. Okay, any other questions? So if not, I would like to start with talking about mathematics. The starting point of this course is in a little awkward position. Oh, let me first tell you what we're going to cover in this course, maybe. A new page. How do I get a new page here? Let's see, maybe here. So we're going to divide this course basically in 2 parts. The first part deals with vector calculus. And this is really something that you can't live without as an engineer and physicist. It's very important to know about vector calculus, and what we will cover is we will talk about 3 basic operations: gradient, divergence, and curl, and then we'll set up these integral theorems that tell you how you can pass from integrating over a line to integrating over a surface, and integrating over a surface to integrating over a volume. And we'll talk about all of this. Okay, so I think this is really very important for your life as an engineer. And then the second part will be complex analysis. And this is really very close to my heart. It's a very interesting subject. And we really start from scratch. We start from 0. And we'll discuss in the end contour integrations. And this is a very important subject. Although it seems to be very mathematical and very theoretic in the beginning, it's really something that you can use. And I was on the PhD committee of one of my former students in this course last semester, and he had basically used all of this in his thesis. So I think it's really very useful for you, although you might fail to see the use immediately. And it's at the same time a very nice opportunity to see how a mathematical theory is built up. And this is really something I will tell you when we come to that. Okay? So today I would like to start with vector calculus. And I start in the middle of chapter 9. And the reason for this is that I'm just saving some time, because I think everybody in this room and everybody online will know how to deal with vectors by now, right? So we'll not go over the real basics. We'll start with chapter 9.7, which is gradient of a scalar field. And maybe I should just give you a brief overview before we start talking about the gradient of a scalar field. I'll just write the title. So this is 9.7, and it's also a directional derivative. Okay, so we will deal with vectors, right? And just to fix the notation, let me just briefly remind you that if we have a vector in 3D, I will, in the following, always use these unit vectors I, j, and k to write the vector, right? So I will write it as vx times I plus vy times j plus vz times k, okay? And I, j, and k are just the unit vectors in the three directions, x, y, and z, right? So if this is x, this will be I, right? And then, let me just make this a little bit longer. So if this is the y direction, this will be j. And if this is the z direction, this will be k. And these are just vectors having a unit length of 1, okay, pointing in the three standard directions of the Cartesian coordinate system. So if we are in 2D, basically, we call this vector v or w. So this would be wx times I plus wy times j. Okay? So what you should know is how to add two vectors, how to subtract, and I think you all know this, right? To add and to subtract. And if you're unsure, you can just read through chapter 9, okay? Everything is explained in the first few parts of chapter 9. What I would like to write down explicitly are two ways of multiplying vectors. So we know two different ways, okay? So multiplying, there's the dot product and the cross product, and they do different things, okay? The dot product takes two vectors and produces a scalar quantity out of them. So if you take two vectors, A and B, and you take the dot product, you all know how to write this down, I suppose, right? So it will be AX, BX, plus AY, BY, plus AZ, BZ. And you see from this result that this will be a scalar, right? It will just be a number, not a vector anymore. So you take two vectors and what you produce is a number, okay? So this is called the dot product. And then we also have something else that takes two vectors and produces another vector, and that is called the cross product. Okay, so A cross B. So this is called the cross product. And in coordinates, this is just the determinant of, if you write the following matrix, AX, AY, AZ, BX, BY, BZ, right? And you take the determinant of this, and we can write this out. Let's see if I can add a new page. Okay, so this just gets a little bigger. That's nice. So I can write this out as AY times BZ minus BY times AZ times I, right? So you just take the standard way of taking the determinant of this matrix, okay? And then for the J component, you get minus AX BZ plus AZ BX. And this multiplies J, okay? And then for K, you get AX BZ, sorry, BY minus AY BX times K. Okay, so this is the way you take the dot product. The cross product. And you see from the result that this is really a vector. And the reason I'm stressing this so much is that this gives you a nice double check. Every time you do a calculation in vector calculus, you should check your result whether it has the right form, right? Whether it's a vector when it's supposed to be a vector and it's a scalar when it's supposed to be a scalar. Okay? All right. So any questions so far? So if you feel unsure about this, just read through chapter 9 for yourself and you will be fine. It's all explained very nicely. Okay? So let me start to talk about the gradient of a vector field. I can switch back to the view. So the gradient is actually taking a scalar function and producing a vector out of it. Okay, so it's a map that takes a scalar function maybe in full generality will deal with 3 coordinates, right? So f of x, y, and z, and it will produce a vector function. Okay, vector function. I say vector function because it will still be a function of x, y, and z in the most general case. Okay, so if we take a scalar function f of x, y, and z, and we take this differentiable, and we require that it has continuous partial derivatives, then we can write down the gradient. Okay, partials I use as abbreviation for partial derivatives. Okay, we can write down the gradient, and the symbol is this nabla sign. Okay, gradient of f, or sometimes I write grad f. This is defined to be df dx, partial derivative of the scalar function f with respect to x in the I direction, df dy in the j direction, plus df dz in the k direction. Okay, so you clearly see this produces a vector. You start with the scalar function f, and then you produce a vector that has these 3 components, right? Let me give you an example. So this is really very simple, right? You just take derivatives, and I hope everybody knows how to do this, okay? The example is in 2D. So in 2D, you would just forget about the third component, okay? So if you have a function f of x and y that has the following shape, e to the x sine of y plus y squared. Okay, this is a perfectly fine function. You can ask for the gradient. Okay, what is the gradient of f? All you have to do is find partial derivatives, right? So let's write down the 2 partial derivatives, df dx. Well, if you look at this function, you have to use the chain rule, right? And the chain rule is also summarized in 9.6 if you're unsure about it. So if you take the chain rule, you have to take the outer derivative of the exponential first, right? So this will reproduce e to the x sine y, okay? And then there's an inner derivative of x times sine y, which will just bring a sine y down, okay? E to the x sine y. And the y square gives you 0 if you take the derivative with respect to x, okay? And then we have df dy. So it has the same outer derivative, right? The inner derivative will give you cosine y times x, okay? If you take the derivative with respect to y, e to the x sine y, and then the y square will give you 2y, okay? So these are the 2 partial derivatives. You plug them into the definition, you get the gradient, and sometimes we like to calculate the gradient at a particular point, right? So let's pick the point 2 pi over 4. So this means x is 2, y is pi over 4, right? Then we can write down the gradient of f as df dx evaluated at this point, okay? Sine of pi over 4 is 1 over square root of 2. So it's 1 over square root of 2 times e to the x times sine y. X is 2. 2 times 1 over square root of 2 is square root of 2, right? So e to the square root of 2. And all this multiplies I, okay? And then for the j component, we put the same points in here in the y derivative, okay? So x times x is 2. 2 times 1 over square root of 2 is again square root of 2, okay? Times e to the square root of 2. And then the 2y give us 2 times pi over 4, which is pi over 2, okay? And this multiplies j. So this would be the vector that represents the gradient of f evaluated at this particular point, okay? And all of this, let me write down sine of pi over 4 as 1 over square root of 2. And this is the same as cosine of pi over 4. Okay, any questions about this? I think it's pretty straightforward, right? It's not really very troublesome. You just take the definition and you plug it in, okay? So this brings us to the next point. What you can write down once you know how to take a gradient is what is called a directional derivative. And this is very useful because it allows you to define a derivative in a certain direction in space, right? If you're just in one direction, all the derivatives will just be in x direction. But if you're in three-dimensional space, sometimes you would like to find the derivative of a certain function in a certain direction in space. And this is what the directional derivative does. Directional derivative, okay? It's called dB of f, so it's also of a scalar function. So we're always dealing with a scalar function f, okay? So it's called dBf, or in another notation, we sometimes write df, ds, df, dB, well, of, let's keep this notation, of a function f of x, y, and z at a point. So it's all related to a point, right? It's in a certain point P, in the direction, I still haven't told you what this little b is, right? In the direction of a unit vector b. So this b gives you the direction in which you would like to calculate the derivative of the function f, okay? And this vector b is in standard notation bx, I, by, j, bz, k, okay? So the directional derivative at a point p in the direction of a unit vector is defined to be the following. We write dB of f at a point x0, y0, z0. Okay, so this point P is specified by the three coordinates at this point. Okay? And it's, well, the mathematical definition is, of course, very abstract, but we'll give you another definition in a moment. Okay, so it's defined as the limit of t going to 0 of the following quantity. I take f and I evaluate at x0 plus bxt. So I go a little bit away from x0 in the direction that is given by b, by the vector b, the x component of the vector b. Okay? I do the same thing for the y coordinate. I go a little bit away in the direction that is prescribed by my vector b, that is a fixed vector, right? And I do the same, I do the same in z direction. z0 plus, oh no, I messed this up, I'm sorry about this. by times t, z0 plus bz times t, okay? So I take a small parameter t, and I go in the direction that is prescribed by b, and I subtract. Maybe I should have written this a little bit more condensed here. I will get to this eventually. bz times t, okay? And I subtract f evaluated at the point itself. x0, y0, z0, okay? And all of this I divide by t. So you see this is very similar to what is called the differential quotient in differential calculus, right? So what it means geometrically, you can imagine in three-dimensional space, okay? We fix a point P that is given by its coordinates x0, y0, z0, right? And then we go into the direction of B by an infinitesimal amount t, okay? So we go in the direction of B, so let's assume this is the direction that's prescribed by B, but we don't go all the way, we just go by t times B. We go a little bit, and little bit is given by the amount of t, right, in the direction of B to a new point that is x0 plus bxt, y0 plus byt, z0 plus bzt. okay? And if we let this t tend to 0, this means we're really looking in the vicinity of this point x0, y0, z0, but we are calculating the derivative of this quantity in the direction of the vector b, okay? So this is the mathematical definition, and of course it's a little bit abstract. So we would like to have a better handle on this, because this is hard to calculate, right? If I would ask you to calculate the direction derivative of a certain function, you wouldn't like to start evaluating these limits, okay? So this is the same. Let us derive another form of this directional derivative, so we can note that this is the same as the derivative with respect to t, right, of f of x0 plus bxt, y0 plus byt, z0 plus bzt, okay? This is just the derivative of this. It's just the differential quotient that you would like to write down if you write down a derivative, okay? But there's another way of calculating this derivative, namely we can explicitly do a calculus of differentials here, okay? And we can explicitly write down what this quantity is, okay? So if we would take the derivative of this quantity, we would have to use the chain rule, okay? So by the chain rule, this is also the following expression. Well, you would take the first component, right? You would take the outer derivative, df dx, and then you would take the inner derivative, and the inner derivative would bring out a factor of bx, right, if you took the t derivative. So by the chain rule, this derivative would be the same as bx times df dx evaluated at x0, y0, z0, right? And then if you have a function of several derivatives and you take the total derivative, if you have a function of several variables and you take the total derivative, you have to add all the partial derivatives together, right? So we have to add the y derivative, which gives you an inner derivative of by, right? df dy at x0, y0, z0, okay? And then you add the z derivative, bz, df dz at this point, right? x0, y0, z0. Okay? But if you look at this expression, it has a very familiar form, right? I don't know if you recognize this, but this looks exactly as a dot product between two vectors, namely one vector that is our b vector that we started with, and the other vector that is a vector containing the three partial derivatives. But we know what this vector is, right? It's the gradient. It's what we have written down previously, okay? So this is really nothing else than the dot product between b and the gradient of f, okay? And all of this evaluated at x0, y0, z0, okay? And this is, of course, much easier to handle, right? Because everybody can find the gradient of f and take the dot product with a vector b. So this allows you to avoid this limit definition for the directional derivative, right? So the upshot is that we can write a formula for our directional derivative, and we can write this as b dot gradient of f, okay? So this is the formula that is of practical use that you can employ every time you have to calculate a directional derivative, okay? Keep in mind that this vector b is actually a unit vector, right? So I just wrote this down. I didn't stress this so much. So this is if b is a unit vector, which means it has a length of 1, okay? If it doesn't have a length of 1, we have to divide by the length of the vector, right? So if we would take another vector a, well, it's not the 0 vector, okay, is not a unit vector, a unit vector, and we would calculate the directional derivative in the direction of A, dA of f, we would have to divide by the length of A. Okay, this is just the definition. So we would have to take the dot product between A and gradient of f, but we have to divide by the length of A. Okay? So whenever I ask you to take the directional derivative in the direction of a vector that's not a unit vector, you're supposed to divide by the length of A. Okay? Any questions? So let me give you an example. Let's take the following function of x, y, and z. 2x squared plus 3y squared plus z squared. Okay? And we would like to calculate dA of this function f at P, and P is the point 213, okay, in the direction of A, and A is given by, I sometimes write vectors with these square brackets, okay, so that these are the three components of A, 1, 0, minus 2. Okay? So this is an example where the vector A is not a unit vector, which you can see immediately, right? So you should know how to calculate the norm of a vector, right? You just square all the components, you add them up, and you take the square root. So let's calculate the norm of this vector, right? It's square root of 1 square plus 0 square plus minus 2 square, right? So it's square root of 5. Okay? So we would have to use the second definition here and divide by the length of A. Okay? So to find the directional derivative, we first have to calculate the gradient of f, and we know how to do this, right? Gradient of f is just a vector that contains all the partial derivatives. So the partial derivative with respect to x is 4x, okay? 4x. With respect to y is 6y. And with respect to z is 2z, okay? And then we evaluate at P, okay? So gradient f at P, we plug in the coordinates of P, right? So x is 2, which makes this 8. And then y is 1, so this is 6. And z is 3, so this is also 6, okay? So this is our gradient evaluated at the point P, and then we can find the directional derivative of f as 1 over the norm of A, 1 over the length of A, right? 1 over square root of 5. And then we have to take the dot product between A and grad f, right? So A was 1, 0, minus 2, okay? And grad f was 8, 6, 6. Okay, if we take the dot product, it's 1 over square root of 5. 1 times 8 is 8, plus 0 times 6 is still 8. Minus 12 is minus 4, okay? Times minus 4. And you see that this gives you a number, right? This number represents the directional derivative of this function f in the direction of the vector A. So it tells you exactly how this function f changes if you move in the three-dimensional space in the direction of the vector A, right? And you could, for example, think of a practical example, a temperature distribution, right? There's this problem that always comes up. You have a strange planet that you're exploring, right? And you would like to map the temperature distribution, so this would be the function f. And you would like to know in which direction the temperature changes in a certain way, so you would test different directions, and you would calculate directional derivatives of this. And you would know in which direction the temperature changes very much or not so much, right? Any questions about this? So this brings me to the next topic, right? that gives you a little bit an idea about the properties of this directional derivative. So I gave you this example of this temperature distribution. It would be nice to know in which direction the temperature changes the most or the least. And there's actually a general answer to this question, right? Because you can say that the largest directional derivative will always occur in the direction of the gradient, and the smallest will always occur in the direction of minus the gradient. And I will explain to you why, okay? So this is one of the two fundamental properties I would like to discuss about what you can do with a gradient, okay? So there are two fundamental properties. And I'm afraid we won't be able to cover all of those today because we only have 10 minutes left. So, but I will nevertheless write them down for you first, okay? So that we can say that the largest directional derivative will always occurs in the direction of the gradient, And this is something that's very important, right? So if you have a height profile, for example, for a mountain range, right, you would know in which direction the height profile is changing the most, namely in the direction of the gradient, and this is where the water will run down, right? So this has very practical implications. It might be very theoretical, but if you picture a problem where you would need this, you immediately see the practical purpose of this, okay? And the smallest directional derivative always occurs in the direction of minus the gradient. Occurs in the direction of minus gradient f. Okay? So why is that? Well, there's a very simple reason, okay? So why? If you write down the dot product, if you look at the formula for the directional derivative, it's always given by a dot product, right? So if you look at the dot product of two vectors, u and v, right, you can also write this as the length of u times the length of v times the cosine of the angle between the two, right? I don't know if you remember this. We have two vectors, u and v, okay? You have an angle between them, theta. You can write the dot product in this way also, okay? Where theta is between 0 and pi, okay? 0 and pi, okay, is the angle between u and v, these two vectors, okay? So if you look at the definition of the directional derivative, it's the dot product between a vector that you fix and the gradient, right? And this dot product will be largest if the cosine is largest, right? When is the cosine largest? Well, it's largest if theta is 0, right? If you picture the cosine between 0 and pi, right, it's a function like this. So the result of this dot product will be largest when the cosine hits 1, right? And it will then decrease monotonously, right? So this dot product that gives you the directional derivative will be largest if you have an angle between these two vectors that is 0, and this means that b is in the direction of the gradient, right? So this will be the largest, the point where, or the direction in which we have the largest directional derivative, okay? So let me write this down. The largest directional derivative at a certain point, at a point P, occurs in the direction where the angle theta is 0, right? Occurs in the direction of gradient f, right? Where theta is 0, okay? And with the same line of reasoning, the smallest will be when the cosine of theta is -1, right? And this is when theta is pi, and this means you're in the opposite direction of gradient of f. Okay? So the smallest directional derivative at p occurs when theta is pi, right? And this means minus gradient f is equal to b. Okay? So it's a very simple reason, but it gives you a very nice way of telling in which direction you have the largest or the smallest directional derivative. Okay? Let me give you an example for this. We might be able to just finish this example. So let's pick up our old function where we already know what the gradient is to help us calculate things. Okay? Plus y squared, and we put ourselves at the same point as before, 2 and pi over 4, okay? And we would like to know what is the unit vector where the biggest directional derivative in the direction of the largest directional derivative, okay? Unit vector in the direction of the largest directional derivative. So we just said the largest directional derivative will occur in the direction of the gradient, right? So this will be the gradient, right? B will be the gradient of f, and we calculated this previously, right? It will be 1 over square root of 2 e to the square root of 2 times I, okay? Plus square root of 2 e to the square root of 2 plus pi over 2 times j. Okay? But since I asked for the unit vector, we have to divide by the length, right? And the length is just the square root of the square of this, right? So it's 1 over square root of 2 e to the square root of 2 squared, right? Plus square root of 2 e to the square root of 2 plus pi over 2 squared, right? And we have to divide by this, right? So b divided by the length of b would be the answer, right? So it would be, this is the length, be gradient of f divided by gradient of f norm, okay? What would be the directional derivative? So dB of f at this point p would be the gradient of f, the dot product between b and the gradient of f, right? So you would take the dot product of the gradient of f with itself, which would give you the gradient f norm squared, divided by the gradient of f norm, right? So this would just give you the square root of 1 over square root of 2 squared plus square root of 2 e to the square root of 2 plus pi over 2 squared square root, right? This would be the largest directional derivative which occurs in the direction of the gradient, okay? So time is almost up. Let me just mention, I said there are two fundamental properties for the gradient. The second is that the gradient will always be perpendicular to level curves or level surfaces. So let me just mention this briefly, and then I will comment about this next time, okay? So if we are in 2 dimensions, the gradient will always be perpendicular to what is called a level curve. And a level curve is a curve where f of x and y is constant, okay? That's called a level curve. And in 3 dimensions, the gradient is perpendicular to a level surface. And this is the same, right? It's a surface on which this function is equal to a constant, okay? And we'll talk about these two phrases next time, right? Just keep in mind that these are the 2 fundamental properties I talked about, and I will elaborate on this next time, okay? So I will let you go for today. We have 30 seconds left, so this is a perfect ending. So I see you back on Wednesday, okay?